and I will try to walk through some of the materials that we presented in our training, which is happening yesterday, today, and tomorrow for the Lower Mekong hub. So there is a little overlapping with the materials. So let me share my screen with that. I already pushed all the materials in the shared drive biplog for your convenience. But yeah, if you have any question on that, I'm happy to answer. I guess my screen is visible to you, right?
Yep, I can see
Yes.
Great. Yeah. So this is like just a brief introduction, the model. So I'll go one by one. So first I'll talk about a little bit of the introduction, and then I'll go through the variables or the features that we used to train the model. I'll talk a little bit about like development and validation with the accuracy assessment of the model. Finally, there's like a little bit of operationalization side or the implementation side. I see a lot of hub people here, so it will be an interesting walkthrough. So yeah, I'm very new in Google Team, and like it is showing me a notification every time. I don't know. So yeah, when I started reviewing the literature in the Lower Mekong region to see like what studies have been performed in this region and what the things that we can do. So the left map is showing a little information on like landslide susceptibility in the Lower Mekong region. And the map you can see is like the susceptibility map. It's actually grabbed from the global landslide susceptibility map, and inset figure is showing the susceptibility area for the whole region. So interestingly, you can see like also like we have the fatalities, number of fatalities within the Lower Mekong region for different countries in the same inset figure. So this is just like carry the information is that this is a highly susceptible region, and we can do a better job in landslides modeling, risk assessment, and all the related activities in this region. So the missing parts that I found within this region is that although a lot of studies has been published in this region, but still there is a lack of reliability on a specific model, because for the region, for a specific region, say in a very small region in northern Vietnam, they used a particular model and they found that that performed very well. But the same model was not used in Myanmar region or Thailand region. So every of this region was having different models, and also like there's lack of inventories. I would say like a lack of accessibility to the landslide inventories. That's another issue to have a complete modeling framework for the whole region. Also, like the triggering variables such as like topographical, hydrological variables, all those data sets are missing in there. Finally, one more thing is that computational resources constraints in that region is a big issue in any decision support system or risk management system. So these all four components, if I now summarize, like how we incorporated in our LHASA Mekong is that for the first solution, like reliability of a model, we use this first ever dynamic landslide hazard and risk awareness system that has been used in our by our NASA landslides team for the global studies. And we found that this machine learning based algorithm that used to study the global landslide susceptibility has an accuracy almost double to the conventional methods. And for the second and third difficulties like the inventory and the relevant hydrological and the meteorological or topographical variables, we used all the NASA and other agency provided satellite data sets and modeling reports to minimize that difficulty. And for the computational resources, we use this Google Cloud platform to minimize the dependency on the locally available resources. And finally, one more thing is that it's a co-development effort between NASA and Hub, ADPC specifically. So yeah, now I will go through like the inventories that we used inside our model is that that was the second limitation that I was mentioning, that we don't have access to the inventories. So for this purpose, for this project, what we did, we used the inventory generated from the satellite imagery. We used Salat 3D algorithm, which is like a semi-automatic landslide detection system. And for this purpose, we use sense detection method, in where we use the pre-event imagery and post-event imagery, and then like different like then a machine learning algorithm to detect the changes, and finally use that one to detect the landslide inventories. The left panel is showing the locations where we have those landslide inventory prepared by using this algorithm. Our team has worked on this, especially Pukar Amatya, who is also in this call. So who did this work? And for more information about this one, you can follow the link shared here. So that publication mentioned more detail about the algorithm. And other, beside the landslide inventories, we also used other variables that's necessary for doing any landslide studies. So we use all these variables listed here, like distance to falls, lithological strength, data slope, topographical wetness index, relief, distance to roads, rivers, all these static variables that we used. And then here I'm going a little faster because this presentation was made for the hub. So I don't think that we need all the information. So these are just like showing all those different variables that I mentioned as the static variables. So this is distance to roads, rivers, and maximum TWI. And beside that, we use two dynamic variables. This is the same way that we model for the global LHASA, but the difference between these two is that the data sources and how we incorporated the data inside the model. So we used rainfall from NASA's EPM IMARS precipitation. We used a combination of early and late run product. So what we did, like we took the last 3 days precipitation, accumulated it, and put inside the model as a variable named as precipitation. So we get this product from partly it is available in Google Earth Engine and partly available outside of Google Earth Engine. So we combined them together to make this 3D accumulated precipitation. And for the soil moisture variable, we use climate forecasting system provided soil moisture data. The positive side of this data is that it is available in Google Earth Engine, and for my past almost 2 years experience, I never saw a missing data or missing or a big latency of this data in Google Earth Engine. And the variable that we grabbed is volumetric soil moisture content. This dataset is available at 6-hourly scale with 25 kilometer spatial resolution. So these are two variables we used inside our model as the dynamic way. So that means every day these variables are getting updated when we train the model or when we will make a prediction from the model. So this is just showing the more detailed about how we configured the model and what are the methodologies we followed during the configuration, during the training of the model. So here, I want to focus mainly on mainly on a few points. Number one is that we had the landslide inventory spanning from 2015 to 2020. We used 2015 to 2019 data for the training, and we kept 2020 data for the validation purpose. And for this study, we focused on rainfall-induced landslides. So we just focused on the flood season when most of the rain occurs in that region. And for the model configuration, we used a ratio of non-landslide to landslide samples as 100:1. And the temporal frequency of the datasets was daily grid size, a special grid size that, or I would say like the finest pixel size that we used in our model is 1 kilometer by 1 kilometer. So the right panel is just like short detailed methodology of the model, but if I just want to focus on the key points is that on the upper left corner it is showing the two dynamic variables that we used. For the precipitation, we rescaled it to illustrate the local variability, and we use soil moisture along with precipitation as dynamic variable. And lower left panel is showing all the static variables that we used. And upper right corner, it is just explaining the how we use the inventory that I was mentioning. So we used all the landslide inventory we generated using the solid CD algorithm. We splitted them between like training and validation part. So for the training from 2015 to 2019 inventory, we splitted them between 67 and 33%. We used 67% during the training phase and 33% for the validation. And finally, we did another way of validation using the 2020 inventory. And after that, when we found the satisfactory result of the model, we deployed it for the operation prediction. So this is just showing, the left panel is showing like the intercorrelation between the variables that we selected. So basically here I'm showing the most important four variables that we found, which is like precipitation, relief, slope, and soil moisture. Among them, precipitation and soil moisture are the dynamic variable, and maximum slope and relief are the static variable. If you see the precipitation named as rescale, because as I was mentioning, we rescale the precipitation. So how we did that, like we took the 3D accumulated precipitation and we actually feed the 3D accumulated precipitation for 20 years in a log normal distribution to get a 99th percentile of precipitation. So finally, we use this 3D precipitation and rescaled it with that historical log normally fitted 99th percentile precipitation. I'll explain a little bit on that when I will walk through the program. But for now, these are just showing like scatter plot, histogram, and contour plot of this like contour plot among these variables. So in the upper right corner, it is just showing the scatter plot. The corner plots are showing the histograms, and lower left corner are showing the contour plot. Here, for the different colors is denotes like the blue color samples are over the non-landslide grids, and the orange color samples are over the landslide grids. On the right corner, I'm just showing like the model results. So the upper right corner, it is showing the Fisher importance plot in terms of gain. That means like if we use the each of these variables, this is the percentage gain, the model accuracy gain through using this variable. For example, precipitation, we found more than 35%. The same way like it is shown as in the figure. So we found like precipitation, slopes, soil moisture, relief, lithology, all these variables was having very high like sequential importance on the model output. And the ROC curve is showing here, which is just like to illustrate the relationship between true positive and false positive rate. And the area under the curve we found for this model was around 0.98 for the optimized configuration that is selected for deployment. So after finishing the training part, we did individual event assessment. So these are some results from those individual assessments. So the left figure is showing the model output on 2015 July 30. So the like different color is showing like different hazard probability level, and the black dots are showing the actual landslide inventory that we created using the solid CD algorithm. So the middle one is over Laos. It's an Jamnu inventory, I guess. Yeah. So this is like, yeah. So this was also like showing the same pattern, and like the right one is showing on the northern Vietnam region. So the true positive rate also mentioned in here. So we found it pretty good results for all these inventories. But to me, it was anticipated because these are the inventories that we used inside the model. Then what we did, like we did validate the model for 2020 inventories. Interestingly, we did not use 2020 inventory inside the model training phase. But still, I would say like we got a pretty good results, as you see from the TPR, like true positive rate results. So one thing I want to mention here is like all the gray color shown as the hazard probability map is showing non-landslide. So we define like non-landslide, and we like classified the hazard probability into non-landslide and landslide as like a threshold value of 0.08 that we define based on like our training of the model. So these are the like individual event assessment. For the retrospective performance, what we did, like we did training the model from 2015 to 2020 for each of the day, and then summarize the statistics to visualize and to understand the long-term trend of the model. So the left corner figure is showing like the mean hazard probability length and corresponding precipitation at weekly scale. So you can see like during the rainy season, we are seeing mostly like high hazard compared to the dry season, or like all the high hazard probability values corresponding to the precipitation if you look at the upper panel. And the right one is just showing like different hazard probability map from the long-term simulations. So the first one is showing long-term mean hazard probability for the whole time period, and the right two figures are showing long-term hazard probability map for dry and rainy season. The same pattern as we see from the time series comparison. Like there's a big difference between the dry period hazard map and the rainy flood period hazard map. So after this, like we are, I would say like satisfied with the results that we are getting. So we implemented in Google Cloud Platform. So just to mention, like during the training of the model, we used the local computing resources at our end to train the model using Python XGBoost algorithm. And finally, we put the model in Google Cloud Bucket Storage. From there, it grabs all the variables it is needed, like the precipitation, soil moisture, and the static variables. And finally, make the prediction for every day if you want, or even in the final temporal resolution if you want. And it push the results back to Google Earth Engine, from where users can get access to these results through App Engine or through Earth Engine apps. So yeah, that's kind of this all I had regarding the introduction of the model. So just like to summary, like I talked about like the necessity that why we needed this modeling framework for Lower Mekong region, how we developed and validated the model, how we did the accuracy assessment, and the operationalization. I'll go through the code, but before that, I'm happy to take if you have any questions on this part. Or if you prefer, I can walk through the code and then we can just keep the space for question and Q&A session.
Any other questions right now? If not, we can reserve the time and go right to the code. All right, let's go to the code, the fun stuff.
Okay, sure. Yeah. So let me share another screen so that I can go through the code. So the code that I used here, actually earlier I showed this same code, or I would say like we did a, let me check if I'm presenting or not. Can I see my screen still?
No.
No, okay. Yeah.
Yeah, I just see a black screen.
Yeah, maybe it was just like showing the PowerPoint presentation. Give me a moment.
Okay, I can see it.
Yeah, great. So this is the same code. This is the same like training module that I used earlier to train the hub. Like team and RT was in there. So I will show the same code that how we that is explaining like how we train the model. So yeah, so the way that I did like this is like Google Colab Notebook. I found that this is super easy to demonstrate during any training or like workshop type thing. So here what I did, like first is section, like this is defined, this is like classified in different section. In the first section, I imported all the libraries that is shown in here. So let me go through it. It's one of them. So the only one package that is missing here is called Sharp. So I use this package to visualize the machine learning model. Oh yeah, sure. I can zoom it. Can you see now? Is it better? Yes, great. So the first package that I use, the only package that is not available in Google Colab is the Sharp package that used to explain the nature of like results of machine learning models. So that one thing that I wanted to install here. So I'm just installing that one to make sure that it is available. Yep, now it is available. So now I will import all the libraries here. I explained like why we needed these libraries a little bit, and I kept this notebook in the shared drive Biplov shared with us. So now I will mount the Google Drive. So I will also use 2 or 3 files, or I'll say like some of the information that I also kept in the Google shared Google Drive. But right now it is sitting in my Google Drive, and the directed name is LHASA Ascent Training. So uh, I'll just unmount the drive. So this is the drive that I use here. So I'm unmounting it right now. As we are calling step 1C. And then in the second step, we will load all the data. So here, interestingly, I kept one data set ready for the training purpose, which I named as version 2.0 10 input. So the reason that the way that I prepared this file is like this consists of all the variables needed for the models. That means like all the static variables that I mentioned: distance to poles, distance to rivers, distance to road, slope, relief, topographic wetness index, all the variables are written in there. So I guess that's available in there. What I can check. Let me check. Okay. Give me a moment. Looks like, okay, I can share it from here. So I'm talking about this file. I don't know if it is super big, so it might not be, it cannot be opened from the Google Drive directly. But this file consists of all these variables that mentioned in here. So what I'm going to do, I'm going to print the input so that you can see. So this first line is just like reading that CSV. The second line is renaming the columns because I want to be consistent with the name of the columns. Earlier I used this one, and then later I found that this one is better. So I'm renaming all the columns for the data frame. And one thing that I'm calculating here is like log precip. That means we are scaling the precipitation in this line. So how we are doing that, like for the samples that I prepared, we have the precipitation column, and we are dividing with the P99 of precipitation, which is 99 percentile of precipitation. And for this 99% of precipitation, we calculated using 20 years of precipitation data and then fitted with a log normal distribution. So looks like it is done. So we can just describe the variables so that we can see. So if we see here, these are different grid IDs to understand like individual grids. I put the IDs for the different pixels. We have latitude, longitude, landslides, deep faults, which means distance to faults. We have lithological strength. We have distance to roads, distance to rivers, elevation. Although we did not use this one inside model, but I just kept it in here for the visualization purpose. We have maximum slope, maximum topographic wetness index, mean topographic wetness index. This one also we did not use. Forest gain we did not use, but that's just sitting in that data set. We have relief. Relief means like range of elevation, like range between max and mean within a single pixel. We have soil moisture. We have precipitation. And finally, this is the log precip that I calculated or that I rescaled using the formula that I mentioned earlier. So this will make a plot for us. This is like just for just to visualize the maximum slope. Let's see, it might take a little time to load the figure here. And then after this, we will go for the training of the model. So allow me for a moment to the figure to make sure the figure is popped up here. Yes, it came here. So interestingly, if you see there is like two peaks. Clearly, the first one is over the non-landslide grid, and the second peak of this slope is showing the over the landslide grid. So now I'm going to the training part, as we already have all the variables that we needed for the training of the model. So this is the input research that we finally used to train the model. That's like the log precip, which means rescaled precipitation, and distance to faults, lithology, distance to rivers, distance to roads, slope, relief, TWI, and so much there. So these are the input features that I'll be using. And I'm here, what I'm doing, I'm just like dividing the samples into training and testing. So here I used stratify equal to Y. That means like keep the training and validation sample as the same ratio of Y. Y means here like the landslide rate, landslide events, and we have test size as 33% and validation, sorry, training size as 67%. And I put a random state at 50 so that we can generate the same random number every time. So this part is done. Now this is like the model parameters that we'll be using. So the maximum depth of the tree we used for the extreme gradient boosting algorithm here is 2. One thing that relates to maximum depth of tree is like, I guess I'm correct, Thomas, you can correct me if I'm wrong, but it is more of like for interaction constants. If the maximum depth is more than number 2, then the interaction constant cannot work. So we have like ETA parameter. I would say like I mentioned here, related link you can read through, but the main changes that we made, like changes that, not changes, like main updates or main core component that I want to mention is like, first one is like objective is our objective is binary logistic. That means like we are classifying the data between like 0 and 1, just for binary classification. 0 means like no landslide, and 1 means like there is a presence of landslides. We used like area under the curve accuracy assessment here. This line is showing monotone constraints. That means like this line is defining the relationship with the probability of having landslides and the triggering variables. For example, here 1 means if we go up, log precip is the first variable. That means it has a positive relationship with the probability of landslides. So when riscal precipitation is higher, there is a higher chance of having landslides. So if you see -1, that means like the relationship is inverse. That means if the distance to flow faults is higher, there is a less probability of having landslides. So this is how we define the monotone constraints, and the interaction constraints here is defining the rule that the precipitation is the only variable which can talk to other variable or which can interact with the other variables, because here we are looking for the situation with only rainfall and induced landslides. So this is how we define different parameters. I will not go through each of them, but I pasted the link here so that you can have a look to understand a little better if you are interested. So here we use number of rounds as 300, and the verbose frequency 20 means like after every 20 step, it will show us the statistics. So now I loaded all the parameters here. I'll go to the next step. So here I'm just starting to train the model. We are saying parameters is defined in the upper cell. We have the training data set ready. Number of round is ready, verbose frequency is ready, and the evaluation list is ready in the upper section. And finally, after training the model, we will save it. Let me save it as a name, say log precip training. I'm starting to train the model. It might take some time, but you can see here it is showing like the training accuracy and area under the curve and evaluation accuracy, or I would say like area under the curve values is showing for every of these steps. So this is done for up to 20 steps. Now it is producing result for up to 40 steps. So we need to wait until 300 steps to go for the next step. So yeah, I'll take a pause here. Like I'm finishing this part. But I am happy to take a small question in the meantime.
Any questions on the line? I had one real brief one about sort of the rationale for creating that log precip variable. Is it to handle some of the nuances of the precip itself, or are you actually trying to maximize that the temporal baseline of that data as well? So do you have any rationales to that?
Yeah, that's a really good question, Tim. I appreciate the question here. So what we found from our experience is like initially we planned to use the raw precipitation, but what we found in some location in whole Lower Mekong region, that region automatically receives very high amount of rainfall, and that might not be a rainfall triggering event, right? But in some location there, if you even receive a lower amount of rainfall, you can get a very high chance of having landslides in that region, because that region historically receives very low amount of rainfall. So to defend that, like in some region, it receives historically low precipitation, some region historically receives very high precipitation. So just to differentiate between those two regions, we needed to scale the precipitation. I can show you one quick plot on that. If you just look at here. So if you look on the right panel figure, I think my screen is visible. Yeah, I can see the slides here.
Yep.
If you see here, the historical 99th percentile precipitation, if you see along the coast, it automatically receives very high amount of precipitation. It's like more than 3,500 millimeter of precipitation in a 3-day accumulated scale. But if you look on the like a little far from the coast, it receives very low amount of rainfall. So just to distinguish between these two, we needed to scale the precipitation, because it is just telling the model that, hey, this is not the actual amount of precipitation that I'm providing, because there is a like location variability. So we scale it and then we provide it to the model.
Great. Yeah. Thanks so much. That's very informative. I think it's helpful for folks also just thinking about handling data for their machine learning, but also just the nuances that go into the geographic differences as well.
Okay. Yeah, sure. And like in the meantime, our model is done training. So I can go to the folder like Google Drive folder where we save the model. You should come here. So let me check. So this is the one that I used earlier. I'll refresh it. It should come one more file. So yeah, you can see this one was just saved. So this is the model file that we saved from that code. So now it is available. Now I'll go to the next step, which is just for like training result visualization. So this is just one example, because like we have total around 300 trees. So this is just like a particular number of tree I just wanted to visualize. Like if I run it, say I put it 38, let us put a random number to 76 and see the results here. Oh, okay. Oh. So let me check. Okay, that's good. So yeah, maybe there was some technical difficulty that I need to check, but I just wanted to illustrate. This is like the decision tree that I used, that we used inside the model. So this is one single tree that is showing like the leap value is more of related to probability, and like this is like all the variables that you can see, log precip, relief, and it tried with the combination and to produce the results that we are getting. So the next step is like feature importance, is I will say like most informative part of this model training, because it shows like the importance of different features in model output. So this is the results from model output, like the feature importance. But just before going to the figure, I want to mention two things here. So there are like few types of feature importance. Number one is like gain. Number two is weight. Number three is cover. There is like also total weight and total cover. But the one that I am more interested here is to see the gain. That means like how much accuracy model can gain if we use that particular feature or its variable. So here it is showing that feature importance plot in terms of gain. If you see here in the upper panel, it is just printing all the feature importance in different terms like gain, weight, and cover that I was mentioning. But this one I would say like most important one for our purpose. So you see like most important parameter in terms of gain was log precip, and there's like maximum slope, relief, soil moisture, all those variables that used to make that prediction. So finally, this is the like another way to visualize the results. That package that I was talking is like more like a very good use to explain the machine learning algorithm. So this this figure shows like in terms of like the feature importance, the same one that I showed in the earlier section, but it's in a little different way. If you see all these pixels, this is like it is showing individual pixels, and the more red color showed like very more like higher importance, and the blue color is showing like low importance. And like the scale here, it is showing like if it is left to zero value, that means that particular feature has a negative importance, And if the value goes on the down right side from the zero value, that means that feature has a positive importance. For example, if you look at here log precip, like it is showing very high importance because of the color, and this, it is showing on the right side of zero values. The same way, if you look at the distance to roads, it is showing like more negative relationship with the landslide triggering variables. There are still some inaccuracy, I would say, from the precipitation side or like the relief side, or like almost like for all of the variables. There are a few reasons for that. For first reason I want to explain is that like during taking the non-landslide samples for the training of this model, we pick the random grids within the whole Lower Mekong region. Those are the grids are not covered as landslide grids, but those are random grids. So there might be landslide, there might not be landslides, which we are not sure. That's like another way to incorporate some noise inside the model. But again, like if we had more distributed landslide inventories or like more information on non-landslide grids, that might this part might be a little better, but still we are happy to see whatever we got. So the next section, I am just plotting the ROC curve, like the receiver operating characteristic. So this is like just showing the relationship between the true positive rate and false positive rate. So like as I mentioned, as like to explain the figure, like if you see this blue color close to the axis, that means the model is perfect. And if the blue curve is close to the red dotted line, that means model is like the accuracy is so low. So we are happy with the accuracy that we got from here. But yeah, that's kind of all I wanted to walk you through for the codes as we are done with the training of the model and like the results that we are getting. So I'll keep some space for QA session and I'll stop here.
Well, thanks so much, Nishan. That was fantastic. I'll pause right here. Any questions on the line? Go ahead, Biplav.
Thank you, Nishan, for your detailed presentation and walkthrough of the code. I think it's very helpful and appreciate your time. I have 3 questions. I think I might have missed this, but can you talk about how you're collecting your label datasets? Like, are you hand drawing them or you're getting from some repository? And okay, I can go on the next question and you can maybe answer.
Sure.
So the next question is, it's linked to the first one. So in one of your slide, you saw the ratio of landslide and non-landslide data was like 100:1 or 1000:1. So could you talk about this class imbalance and how this could have affected your model and how you're probably incorporating that quantitatively? And the last question is regarding to like, why did you pick an XGBoost as opposed to like a random forest? Like most of the people, the first choice would be go to random forest or some simple decision tree. Thank you.
Yeah, great. So I think, can you repeat the first question?
I think Pukar could answer the first question. It's it's about the mapping process for inventories.
Sure. I thought that's like the hydrological variables. I'm sorry. So yeah, I can just fill up the slides.
Just confirming with Biplav, are you talking about like inventories or?
Yeah, or the hydrological data or the topographical data that we use.
I'm talking about the landslide inventory.
Okay.
Yeah, sure. So like, I guess like during the start of the projects, like there were talks of like country maintained inventories that could be shared with us, right? So I know like for a fact that there are like detailed inventories from Vigmar in Vietnam and then DMR in Thailand. So at the end, the beginning of the 3rd year, we did receive an inventory from DMR Thailand, but this LHASA 2.0 model is set up in such a way that having just landslide inventories are not enough. We need to have event-based landslide inventories. By what I mean by that is, like, correct me if I'm wrong, Thomas, but what I meant is that we also need the date of the event. So what I did was like, I basically spend a lot of time looking at how to say, like event-based, like rainfall-induced landslide events all across LMR using media reports. And then basically when I know like, hey, this area has like a landslide reported, what I did was like, I just go to Planet Imageries, download pre and post, and then use the Salad CD algorithm to create those inventories by myself. And the advantage of that is like, we also know the date range of when those landslide event happen. So it's basically like me spending some time looking at the events, looking through Planet Imageries, and then once I confirm that there were some landslide that we were able to map, I just run it through the Salad CD algorithm. So Nishan, like if you can paste the paper in the chat, like that would be helpful, I guess. Like it has documented all the steps that I took, like on how I created those inventories. So if you need more information, like yeah, you can visit that paper. But it's just like all those events were mapped or like created by us, and we have released it in a public repository. So if anybody wants to use it in future, then it's just sitting in a public repository, right? So in a sense that like, yeah, we didn't get any inventories that were available or like was there before the start of this project. We created everything by ourselves.
Okay, thank you. It looks like there was a lot of work that went into this. So thank you for
Yes. So I spent close to like 6-7 months like creating these inventories. So these inventories are the foundation for developing this model, right? So I think like I spent quite a considerable amount of time in the first year of the project just creating these inventories. Yeah.
Yeah, and this is a necessary precondition to doing like an empirically based model, like what we're doing, and it's really it's the part of the process that is really crucial and affects kind of everything that you can get as long as you're taking some kind of machine learning approach. So it's really important, and I would say that that's really where the value is, in my opinion. It's not actually in the kind of the data science part. It's really more in your data inputs, and having good quality training data is kind of what breaks a project like this. If you don't have it, you can't get results, or you can't get good results. So it's really the most important thing, and unless you take a totally different approach.
Yes, I guess like if you're looking to like transfer this LHASA Mekong to like other hubs like HKH or like Amazonia, for example, like you do need like the first requirement will be like these kind of dated inventories to successfully train the model. Like training that was done in Mekong and expecting to work in HKH or Amazonia, where characteristics are completely different. So you do need to like spend some considerable amount of time like compiling inventories, not just any inventories that you find available or like have the government agencies provided to you, but like you need dated inventories.
Okay, so I think maybe I can take the next couple questions. Okay, so the first one is about how we picked 100-to-1. And this is basically the same ratio we used for the global landslide model that this is kind of a regionalization of. So I'm gonna share my slide now.
Yeah, sure. I can share my screen.
I just need to rearrange my windows here, I think. Okay, so I actually have a ton more charts like this, but what we're showing here is just an example of the kind of thing I did while I was developing the global model. So basically with like a subset of the training data set, we can look at kind of the various metrics that you might get in terms of your prediction performance, using different fractions of landslides to non-landslides, as well as, and I didn't just look at different fractions. That's why you see kind of multiple data points at each of these markers. I was actually varying both the number and of the landslides and the non-landslides. So we're getting different ratios and different sample sizes. And what we see pretty consistently is that like the standard recommendation for like 50-50 actually doesn't do very well. And my explanation for this is that the model you get if you do that is extremely overconfident. It doesn't realize that there are a lot of cases that are not in its training data where, for example, you had intense rain, but a landslide didn't occur. Just by kind of the construction of the training data set, if you're taking points at random, then you get a non-landslide data set that is pretty easy to distinguish from landslides. So you make the problem too easy, but then when you apply that same model across all of time and space, you actually start seeing lots and lots of exceptions to the rules that it learned in that training data set that you had that was relatively small because it only included, a small number of negative samples. So what we found is that when you're getting up to around 100 to 1, you're getting pretty good results. Now you can keep on going. I'm not sure, we're seeing a decline at higher numbers. I'm not sure if that's just a blip or if that's real, but I think kind of the conventional wisdom that you want 50-50 is definitely wrong. Another thing we looked at, and I actually have a lot of other charts like this. If you really want to see them, I can break out that slideshow that kind of look into not just the landslide ratio, but also like just the hard numbers of like how many landslides you need. So another thing we did is we did a simulation to understand if we retrained the model every year or retrained it continuously, how would its performance change over time? And what we're really hoping there is to show that the model would be robust if we retrained it year after year, and we wouldn't get a lot of fluctuation. So what you're seeing here is like at the first time step, you're seeing just a model that's just been trained on 2015 and 2016. And at the next time step, you're just seeing a model that's trained on 2015 plus 2016 data. And at third time step, you're looking at a model that has 3 years of data. And then finally, all 4 years of data here are being used to train the model. And it looks like maybe there's some sort of fluctuation here at 2 years of data. But actually, what I would draw your attention to is that the range we're looking at is actually quite narrow. So this isn't 0 to 1. We're actually looking at very high performance across the board. So I don't think, I think what we're actually seeing here is model stability over time as you get more and more training data. And it implies that you really only need 1 year of data. Now, keep in mind that at the global scale, 1 year of data still means that you have thousands and thousands of landslides occurring every year. And therefore, it's a pretty big sample size. If you're looking, this wouldn't necessarily hold true if you were only looking at a single province. So if you only wanted to look at one province, say Quang Nam province in Vietnam, you probably wouldn't be able to count on the model you're generating being robust like this, because any given year might have nothing, or it might have a huge event, and neither of those is maybe representative of the overall trend. Okay, so that is one example that goes to the point of what our training ratio is. I'd also point out, well, I'll get to the next one. I want to show you one other example actually, before we get to my next point. So I'll share the screen again. Gotta love the robocalls. Okay, you can see this chart, right? I think you can. This is out of a paper that Robert Emberson wrote. And what he's showing here is the fraction. This is a landslide susceptibility study in Chittagong in southern Bangladesh, actually not far from the Mekong region, in the kind of the Rohingya refugee camps. But he's looking at the amount of data that he's using to train the model. And so you can see that there is relatively consistent performance as you get to using more and more of your data. Pretty good models you're starting to get over at, you know, I don't know, what is this? A tenth of the data, even 100th of the data. And again, we're looking at, I believe, thousands of points. So this is a static analysis. So in this case, he doesn't need to know when the landslides occurred. So it's easier to map a lot of landslides just based off of like Google Earth or something like that. So he's looking at a very small area with a lot of landslides in it, and it is a different kind of model, but I think you're getting kind of a similar result in that it actually, you don't need a ton of data to get a reasonably accurate model. So that study, I'll just paste this into the chat, this one. And this is a random forest model, so it's actually very similar to the XGBoost model that we just talked about. The structure of random forest and XGBoost is basically the same, but how the model gets built is different. So anyway, that's just an example. Another example where you can look at the kind of the ratio of landslides to non-landslides and experiment with it and see kind of how it affects your results. And I would point out that both of these models, random forest and XGBoost, are quite robust to class imbalance relative to some other modeling types. And this gets to your third question, which is why did we choose this model? So this is one of the important reasons for why we wanted to use XGBoost. One of the reasons is that landslide date, this sort of classification problem, is highly imbalanced. So almost all of the time, in almost every part of the world, there are no landslides. So you could get an almost perfectly accurate classifier by just saying, well, there's never a landslide anywhere. Like you would probably do, you might, in terms of just like your mass accuracy, you might do better than either LHASA Mekong or the global LHASA model, just because, at least according to the records we have, landslides are extremely rare. So that is one of the motivators for why we used XGBoost in the model. Yeah, so just to give you an idea of like how many landslides you're looking at, it looks like we're looking around a couple thousand to do this model that Robert was doing a susceptibility map on. Okay. So I wanted to share a little bit more about kind of the XGBoost documentation that I think also goes to the question of why we might want to use it and how to use it as well. So one of the things that XGBoost has that, say, the TensorFlow GBM doesn't is, at least the last time I checked, is something called feature interaction constraints. And so there's this documentation about it. here on the XGBoost docs. You can read about it. But basically, the idea is that we're preventing some trees from getting built. So XGBoost is, as you probably know, builds a series of trees, and taken together, all those trees make a model that is basically an ensemble of decision trees. Each of those trees could be built to use all of the variables that you're supplying, and that's kind of the default position. But what you can do is you can specify different combinations of your variables such that some of them never interact with each other within a single tree. Now, I'd like to point out that this is not as powerful as it sounds, because unless you build a model that has only a single tree, there may be effectively some interaction between the different variables at the level of the ensemble. Even though every individual tree, you have denied the possibility of building a tree that has both variable 4 and variable 0 in this example. Nevertheless, I think it does give us the chance to have a little bit more realism in what the kind of predictions that the model is making, relative to just taking all the variables and throwing them in the blender and seeing what comes out. So I know we're hitting the end of the hour, Tim. Do you want me to keep going, or do you want to wrap it up now?
I think just kind of closing thoughts as well. I know I knew we were going to run out of time because this is like so perfect for the TensorFlow working group. I want to go over to Miguel real quick because I know we're already a few minutes past. Go ahead, Miguel.
Yeah, thank you, Tim. Actually, just more than a question, is a comment, and to congratulate Tom and Nishan Pukar for this amazing work behind LHASA 2.0. You know, despite the the limitation for the data availability in the region, you guys sorted to like this amazing bureaucracy behind in the region, and then with those amazing technology that you perfectly describe, it shows how scalable LHASA is in other regions. So yes, congratulations for the team, and then yes, thank you for the presentation.
Thank you so much, Miguel. And I would just, I guess my closing thought would be that there's a lot more to be done with making physically realistic ML models. And I'm open. I feel like I have ideas I don't have time to pursue. So, if you guys are interested in future collaborations, reach out and maybe we can talk about them. And I'd also point out that we didn't have time today to talk about SALAD, which is the semi-automated landslide detection model that Pukar used to build the inventory. So if you ever run out of topics, that's another possibility.
Yeah, sure. I'm actually creating a training model for the Bangkok in-person meeting. So Tim, if you want to learn more about SALAD, I would happy to do it in 2 months' time or something like that with the training.
Yeah, that sounds wonderful. As you guys know, I mean, this group is here for all these really sort of technical conversations. So you guys are welcome to attend, any future TensorFlow call. But I would really, really love to just continue to have you guys come in as you're, coming up with new technical aspects, especially SALAD, as was mentioned. I think that detection algorithm could be really, really exciting for the folks here because, we're primarily using Earth observations from NASA, and I think relying on something like Planet could be really cool because we have a lot of access to that as well. So just some other avenues that I think this group across all of Severe could be really excited about. But I know we're well past, and we barely scratched the surface. But I just want to say thank you guys so much. It was really fantastic presentation. Really, thank you for your time. I know you guys are very busy this week, so thank you. And I think we can close there.